Okay. All right, so we're taking a break from that because that means nothing to you. You have no motivation to learn how to take derivatives if you don't know what they're used for. So this recording is just illustrating how this can be used to do stuff. All right, derivatives. Why would they be useful? Okay, suppose that maybe, let's think of a silly data set to deal with. Suppose you have maybe maybe like weight. And again, this is made up, completely made up. But just suppose you have like weight measurements versus blood sugar level or something like that. So we have some measurements of people that we've like observed in some clinic, and for a given weight, we measure some blood sugar, whatever. Okay, this scenario set, y'all okay with this? So like maybe there's like someone like there, and there. We good? Hopefully you find this interesting. We're going to use calculus and derivatives to make predictions about if you're a given weight, what your blood sugar level will be in this made up scenario. Okay. So what do these points look like? So our data set looks like maybe like 1 unit here, 2 units that way, 1.5 units, 2.2, 2 units of weight, 1 unit of blood sugar level, and then 3. And our goal is to use this data to make predictions on data that we haven't seen. Like, for example, none of us participated in this study, so if our given weight, we'd want to be able to predict the blood sugar based off of these people that were in the study. And this is where calculus comes in. So basically what we're going to do is we want to find a line that approximates the data that we have. We want to learn a line that hits this data. We want to find this. Right? The best line that we could possibly find to model that data. Why would we want to know that line? Well, once we know that line, we have an input and an output for the line. So if that person weighs 2.5, then they have approximately that blood sugar level. Does that make sense? If we find the best line, we'll be able to make predictions.
Yes, sir.
Okay. So what makes up this line? This line is really y is equal to, and we're assuming that the line passes through the origin, right? If you have 0 weight, then you have 0 blood sugar, whatever. So it does go through the origin. There's no intercept. The intercept's 0, I mean. Okay. So basically, so what determines that line? Just the slope, right? The slope is the only thing that determines that line. Correct? Like if we pick a slope of 10, it might be like that. If we pick a slope of 1/2, it might be like that, but among all those possible slopes, there is a best slope to pick. Do you all agree that we can?
Yes, sir.
So how can we use calculus to help us find that? Well, let's get clever here and let's make a function. I'm going to call this function C, which takes as input a slope m. And this C function is going to be equal to, bear with me here, 1/2 times, our input is m, right? So m times 1 minus 2 squared plus 1/2 m times our x there, 1.5 minus the y there, m times that x minus that y squared, and then m times that x minus that y. Does anyone get a sense of what this is doing? Basically, this is like our line. That's our predicted line. Right? M times x. That's our line. That's our prediction, and that's the actual value. That's our prediction, that's the actual value. That's our prediction, that's the actual value. That's our prediction, that's the actual value. See, we know the y's, what they should be. And if we choose an m times that 1 better be close to 2. M times that 1.5 better be close to 2.2. M times that 2 better be close to 1. M times that 3 better be close to 3. Does that make sense? This is our line prediction for a given m, and we want that to be close to that. 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 Does that make sense?
Yes, sir.
Okay. Basically, this is our prediction. That's the y. Prediction versus what the y is. Prediction versus what the y is. And we're subtracting it because the worse this is, the bigger this number is going to be, right? M represents the slope of this line that we're trying to find, right? We want a line that hits the data the best we can, and M is the only thing that we have access to, the slope. It could be 10, it could be 1/2, it could be 3, it could be any one of those things, right? And among all those m's, each m is going to predict a y, right? Like m times x is equal to y, m times x, m times x, m times x, m times x. That's the actual y, that's the actual y, that's the actual y, that's the actual y for the respective x's that we input, okay? So if this function was like equal to 0, it would hit every single point if all of this was equal to 0. Right? Because the distance between our prediction and the y's would just be 0 for all of those cases. So this is called a cost function. The lower value this has, the better approximation to that data our line is. Does that make sense? Just checking the chat right now. And like notice like if our m was perfect, this would match up with the 2, that'd be 0. This would match up with 2.2, that would be 0. This would match up with 1, that'd be, if our m was like absolutely perfect. It's not going to be because there is no line that hits every point, but it's gonna, we want to find the best one. We want to find the m that makes that the smallest. And I swear this is all coming back to derivatives. Just bear with me. I'm just really trying to motivate derivatives before we spend the rest of the semester, summer session, doing derivatives and integrals every day, because that's what we're going to be doing. Again, just trying to motivate stuff. Okay. So we have a function. The lower this is, the closer it is to being the best line we can find. Well, what did I just say a moment ago about derivatives? Derivatives tell us where the local extrema are, the local minimums, the local maximums. What type of function is this? This is a bunch of squares, right? Square, square, square. Our variable m is always being squared. So what type of shape does this have, this cost function?
Parabola.
It's a parabola. This cost function looks like this. It's a parabola, which means there's only one extrema right there, which is the minimum of that function. Do you agree?
Yes, sir.
Parabolas have one minimum. So if we find the minimum of this function, where m is the variable, if we find the minimum of this, that means we found the best line that fits the data. So how do we do that? Well, as was mentioned a bit ago, we find local minimums, local extrema, by finding the critical numbers. The critical numbers are the values in the function for which the derivative is equal to 0 or the derivative does not exist. So we need to find the derivative of this function. So it's messy, but we can do it. So dc dm, the derivative of c with respect to m, the 1/2s are there because it makes it nice now. What's the derivative of this first piece? 2 times 1/2 times the derivative of the inside, right? The chain rule. So the first piece, 2 times 1/2, the 1/2 and the 2 go away, and we're left with m times 1 minus 2 times the derivative of the inside with respect to m, which is 1. Plus 2 times 1/2 times the derivative of the inside. So the second piece, the half cancels out the 2. The derivative of the inside is just 1.5, so this will be 1.5 times the inside. Plus 2 times 1/2 goes away times the derivative of the inside, so 2. And then 2 times 1/2, and the derivative inside is just 3. And so that's the derivative of the function. And to find the critical numbers, we set this equal to 0 and we solve for m. That's one way of doing it. Oh, there's no square here, sorry. So if we set this equal to 0, what do we have? It's messy, admittedly. Okay. It's messy, but let's see. I suppose I can. I really want to get rid of these 1.5s and blah, blah, blah. I guess we'll combine my terms. I'm going to go ahead and work it all out. I hate doing this by hand like this. Typically, I'd use a computer and do something called gradient descent, but we can do this by hand. So how many m's do I have? Let's see. Let's see. So we have 2.25 m's here. So I guess I'll just write it out. 2.25 in there. And 1.5 times that is 3.3. Then here we have 4m minus 2, and then plus 9m minus 9. So altogether, how many m's do we have? We have 9, 10m, 14m, 16.25m. And then what else do we have? We have minus 4, minus 13, minus 16.3. And then what does that tell us? Hopefully you can still see. That means that m is equal to this divided by that. 16.3 over 16.25. Can y'all see that? 16.3 divided by 16.25. 3 divided by 16.25. It's like 1.003 approximately. There's our slope. So if we plot that line, so it's like probably like right there, a little bit higher, and then when it's 2, it'll probably be like right there. There's the line that we learned via this. We used the data to make a cost function. We took the derivative. That's the line. So now if someone comes in and weighs at 2.7 units, then 2.7 times 1.03 will be roughly, with some margin of error, roughly their blood sugar level, whatever, in this toy example. So knowing that derivatives tell us the local extrema. Why the derivatives tell us the local extrema? Because local extrema, these bits like this, occur when the slope of the tangent line is 0, which means that the derivative is 0. So if we can find out when the derivative of a function is 0, we can find these critical numbers, these values in our function. If our function corresponds to a cost function, then we can minimize our cost function by finding those derivatives. And if our cost function is set up in such a way that it's using data, we're doing machine learning. That's all machine learning is. It's setting up a cost function using the data and then evaluating derivatives. Everything involving machine learning . 90% of machine learning involves derivatives. And yes, to answer your question, That's the approximate slope. That's the best slope we can find. That is the best slope, to answer your question. According to this cost function, that's the one. Because, why? That function's a parabola. There's only one best choice. It occurs when that's the value of m, which is the best m that we could find for that slope. Okay. Does that motivate derivatives at all? Can I get yeses and nos?
Yes, sir.
Has anyone ever seen derivatives used this way?
Personally, I have
Okay, so I think what I'm going to do, based off of these conversations that we've had, is that throughout this semester, as we're doing the derivatives, as we're calculating derivatives, calculating integrals, what I'll try to do is at least twice a week, maybe once a week, I'll try to come up with a toy or mock scenario where the things that we're learning can be applied to like actual problems like this, just so you can see that what you're doing is actually useful. For example, we just learned what the natural logarithm function is. There's a function called the sigmoid function, which is a transcendental function that's used all over the place in machine learning. Like these logarithmic functions are actually very important to machine learning because they can be used to kind of squish numbers down. And we can talk a lot about how logarithms squish or slow things down next lecture, actually. So what did we do today? Let's go ahead and recap. Introduce the course a little bit. We introduced the natural logarithm function from section 5.1. We learned how to take the derivatives mechanically for these natural logarithms. That led me to ask you why we're taking so many derivatives. I didn't see any satisfactory answers, so then I went on a tangent and basically taught you a lesson from machine learning. So I guess that'll be it for this recording. I'm gonna go ahead and stop the recording.